Modified Gaussian integral I. So this is the third video on our series of modified Gaussian integral. In the first video, we basically had integral from 0 to infinity of e to the power minus ln square x dx. The second one, we had integral from 0 to infinity of e to the power minus lambda w of x dx. And this one, to make things simpler, it's integral from 0 to pi by 2 of e to the power minus tan square x dx. I will link the playlist of all of these videos over here. Do check the other integrals too, and then we can solve this integral. Now let's get on to how do we solve this integral. So basically, if we make substitution y equals to tan x, this is gonna make things somehow simpler, because after this we have tan inverse y equals to x, and we have 1 by 1 plus y squared dy is equals to dx. Yeah, and so we can write this as integral from 0 to infinity e to the power minus y square, and then dx is 1 by 1 plus y square times dy. Yeah, okay. So now let me try to make the power of e also similar, because that will be useful. I will show you how. So I will basically write e to the power minus of y square plus 1 by y square plus 1. But since I have introduced e to the power minus 1 over here, let me also write e over here as well, so that cancels out dy. Now notice that this is just kind of the integral of e to the power ax, because the integral of e to the power ax is e to the power ax by a, isn't it? So observing that, I will try to write this in terms of integral and interchange the integrals, because most of the time interchanging integrals makes things simpler. Yeah, that's why I will try to write this as integral of minus y square plus 1 times t. Yeah, and then dt, such that y square plus 1 is a constant, and the integral from 1 to infinity dy. Now notice that its integral is e to the power minus y square plus 1 t by minus y square plus 1. Yeah, and since this is from 1 to infinity, at infinity this will be 0. Yeah, and minus minus plus, and at 1 this is e to the power minus y square plus 1 by y square plus 1, just as we want. So this works. Yeah, you can check it now. And now we will try to interchange the integrals, because that will make things simpler. I will show you how that makes things simpler. E to the power minus y square plus 1 t dy dt. Yeah, and now let me take e to the power minus t outside, because that's a constant. Over here we just have e to the power minus y square t dy dt. Now this is just again a Gaussian integral, and we know that integral from 0 to infinity of e to the power minus ax square, we know that this is actually equals to 1 by 2 of root pi by a. Yeah, so let's use that. E integral from 1 to infinity of e to the power minus t, and this is 1 by 2 root under pi by t dt. Yeah. So now we have e root pi integral from 1 to infinity e to the power minus t times 1 by 2 root t dt. Now if we let g as root t, this person over here will just be dg. Yeah, so that's why we can write this as e and then root pi, and then root of 1 is just 1, infinity is just infinity, and e to the power this is minus g square and then dz. Okay, and now we know that complementary error function of x is integral from x to infinity of e to the power minus x square dx, and over here multiplied by 2 by root pi. Yeah. So that's why this integral over here is e root pi and then root pi over 2 complementary error function of 1. And so we can write this as e pi by 2 complementary error function of 1. And that's a beautiful solution with beautiful solution development as well. Now talk about the flow. We first made a substitution y equals to 10x, and that made things simpler to look at. After that, uh, we converted to double integral because we saw that the things are actually same, and double integral are helpful to simplify the matrix most of the time. And then we interchanged, which made things simpler in terms of Gaussian integral. And again, we had another Gaussian integral, and that was solved. Well, this problem was somehow sneaky in this step, but other steps were pretty easy. That was it. Also, to check upcoming videos on the modified Gaussian integrals where I will substitute different functions in the power of e. And yeah, I hope you will enjoy such problems. Thanks for watching. Look forward to seeing you in the upcoming videos too.